In this lecture, we'll discuss some key ideas about a very important source of magnetic fields, magnetic dipoles. In particular, there are some key concepts introduced in this lecture that directly relate to upcoming labs that you will do involving short bar magnets as magnetic dipoles. At the end of an earlier lecture on current loops, we began to describe that far from the loop, the on-axis magnetic field looks like that of a dipole. We also introduced earlier the concept of the magnetic dipole moment for the loop, the conventional current capital I times the loop area. Strictly speaking, this is the magnitude of mu. The magnetic dipole moment is a vector that points in the direction of the magnetic field at the center of the loop. To find that direction, we can apply our right-hand rule for currents that we learned earlier. Remember, the way this rule works is you first encircle the current-carrying wire with your right hand, making sure your thumb points in the direction of the conventional current. Then, if you look at your fingertips, treating them as your observation locations, you will see your fingertips point in the direction of the magnetic field. When you apply this idea to the loop, you can encircle the loop anywhere with your right hand, making sure that your thumb points in the direction of capital I. Then, by placing your fingertips at the center of the loop, your fingertips will point in the direction of the magnetic field at the center of the loop, and that is the same as the direction of the vector magnetic dipole moment, vector mu, as shown here. Let's now look at the magnetic field of a loop at locations other than on axis. Another good place to look is on a line that passes through the center of the loop along the diameter of the loop. Such an axis is perpendicular to the symmetry axis we just discussed, perpendicular to the vector mu, so we'll call such axes perpendicular axes. For this particular example, the conventional current, capital I, is still running counterclockwise in this loop. We're going to look at observation locations on this perpendicular axis that are far from the loop, that is, at distances small r that are much larger than capital R, the radius of the loop. Now let's remember in our earlier work on electric dipoles, we examined the field along similar perpendicular axes, an axis perpendicular to the electric dipole moment vector, vector P. And we found this result that at a given distance r from the dipole, E perpendicular is 1/2 the on-axis electric field. It turns out something similar happens for magnetic dipoles. That is, if we are at a given distance small r from the current loop, the magnetic field on a perpendicular axis is 1/2 that of the magnetic field on axis at the same distance small r from the loop. Again, remember, small r is much larger than capital R, the radius of the loop. The direction of the magnetic field on a perpendicular axis can also be found using the right-hand rule for currents. At the part of the loop closest to the observation location on the perpendicular axis, encircle the current-carrying loop with your right hand. For this particular example, you would encircle the bottom part of the loop, making sure your thumb points in the direction of capital I, and place your fingertips of the right hand at the observation location. You'll find that the magnetic field at this observation location points like this. Notice the magnetic field is pointing in the direction opposite to the direction of vector mu. This is a general result for magnetic dipoles. On perpendicular axes of magnetic dipoles, the magnetic field points in the direction opposite to the vector magnetic dipole moment. Let's now look at the magnetic field of a current loop at observation locations other than on axis. and we'll do that with the help of a computer to visualize the field. Here, the current loop, shown in red, is carrying a conventional current, capital I, in the direction shown by the short black labeled arrow at the top of the loop. The conventional current is flowing counterclockwise in the loop from our present point of view. Recall that earlier we used the computer to find the on-axis magnetic field, shown here with a blue arrow. We found this by breaking up the loop into short current-carrying pieces, finding the field due to each piece at the observation location, then summing up the contributions to get the net magnetic field of the current loop at that particular observation location. Let's now repeat this same process for different observation locations, and we see how the magnetic field curves around the loop. Here, just as we expect at the top of the loop, the magnetic field points in the direction opposite to the direction of the vector magnetic dipole moment of the loop. Now, the shape of this magnetic field is not limited to just this view. We see the same shape of the magnetic field for all planes that intersect the symmetry axis of the dipole. So taken as a whole, we can see clearly the magnetic field of a current loop has the characteristic shape of a dipole field. Current loops aren't the only sources of dipole magnetic fields. A common bar magnet that you may have played with as a kid also has a magnetic field in the characteristic shape of a dipole. You may recall that bar magnets have poles, commonly labeled N for the North Pole and S for the South Pole. A bar magnet has a magnetic dipole moment. The direction of the dipole moment vector points from the South Pole to the North Pole. The magnetic dipole moment of a bar magnet is related to the bar magnet's field in the same way as we saw for a current loop. For example, the bar magnet's on-axis field points in the same direction as the vector mu, and for observation locations on-axis far from the magnet, the magnitude of the field is described by the same expression in terms of mu as we found for the current loop. Similarly, for axes perpendicular to the vector mu for the bar magnet, the magnitude of the bar magnet's field on this axis is given by the same expression we found for the current loop. And the direction of the field on a perpendicular axis is pointed opposite to vector mu, just like the current loop. At other observation locations, the shape of the bar magnet's field has the same dipole shape we saw for a current loop. Now, recall for the current loop we had a simple explanation for the source of the magnetic field, the Biot-Savart law for currents, and a simple expression for the magnitude of the magnetic dipole moment. For bar magnets, the explanations are more complex, involving a discussion of what's happening at the atomic scale in the material that makes up the bar magnet. That discussion is beyond the scope of this course. Nevertheless, you will see in lab that by measuring the dipole field of a bar magnet, you will be able to characterize the bar magnet by calculating its magnetic dipole moment without needing to have an explanation of the atomic nature of that field. The Earth is another example of a source of dipole magnetic fields. The dipole axis of the Earth intersects the Earth's surface at locations known as magnetic poles. As you very likely know, the Earth also has a rotational axis. Points on the Earth's surface that intersect with that rotational axis are called geographic poles. Now, the magnetic and geographic poles aren't at the same locations on the Earth's surface, but they are near to one another, meaning the north geographic and magnetic poles are close to one another, and likewise for the south magnetic and geographic poles. And, as you surely know, this fact is used widely for navigation. Now, since the Earth is a magnetic dipole, it must have a magnetic dipole moment vector. And that vector points like this, which means the on-axis field of the Earth points away from the Earth at the south magnetic pole and toward the Earth at the north magnetic pole. Along perpendicular axes, the field must point like this, in directions opposite to vector mu. The lines drawn here give us some idea about how the shape of the Earth's dipole magnetic field must look. One final note. The reason the Earth has a magnetic field is not fully understood today. One notion, which is quite common, that the Earth has a big bar magnet at the center, is not believed to be correct. Presently, most experts believe the Earth's magnetic fields originate from the dynamo effect, where, under the right circumstances, magnetic fields arise spontaneously from the turbulent flow of liquid metals near the Earth's center. That's it for this lecture. In our next lecture, we will introduce a new topic, a way to describe electric fields using energy ideas through the concept of electric potential.